Good afternoon, everybody. Welcome to TechEd 2013. I hope you guys are enjoying the week so far. This is the second session for the day here, so I hope that first session was good and that we can keep going on to this next session. So in this session, this is the indexing fundamentals for SQL Server. My name is Jason Strait. I'll be your presenter for today. I'm a Microsoft SQL Server certified professional and also a Microsoft SQL Server MVP. I've done quite a bit with indexing, and hopefully I can share some of that knowledge with you here today and help you all learn a little bit more about indexing. So for our talk today, what we're really talking about is data. And that's where we start from with this discussion. We're really talking about data and how to get to that data. And the main way in which we want to get to this data is going to be through indexes. Indexes are just one of those things that are extremely important within the database world. They provide the way that you can get to all of your data, and that's just vitally important. And as part of that importance, we really need to have a very good understanding of indexes in order to properly apply them. And through that understanding, we can start to see the impact of what we're doing, because there is an impact to every index that's out there. Whether you have one index on a table or 100 indexes on a table, that mixture of indexes that's out there has a deep impact. And it's very important that you get the right set of indexes out there, because if you don't, then the users of your databases and the managers that you report to are going to be quite disappointed, because they're not going to see out of that database the type of information that's there in the time. And that's where you get the performance that the indexes do provide. And that's what we're going to be talking about today, is how can we look at the fundamentals of indexes to get to this point where you have a highly performing database. Now, as part of this talk, I've broken it down into just three main areas. I wanted to keep it very simple, very fundamental. And so what we're going to be talking about today is, why do we index? What can we index? And then how should we index? And all three of these areas are very important as part of that understanding and the importance of indexes. So for the first section here, why do we index? Well, let's think about, why do we index? Why do we need to go out there and provide these indexes on the database? Well, the first reason why we need to do this is performance. The performance that we gain from our indexes are pretty much the main reason why most people go out and do the indexing. But why do what are we trying to do with this performance? And what we're trying to do is provide that access to data. We're trying to get the users from the queries and the filters that they're providing to the data as fast as possible. And we want to do this by minimizing the number of pages that are accessed. Whether they're data pages or index pages, we want to minimize that. And that's what we're doing with indexes. That's how we get the performance. By doing things like taking 1,000 pages that we have to go through and making it 5 pages. That's where we get our performance. Now, there are some other reasons to do it, and one of those other reasons is troubleshooting. In a lot of engagements that I've worked in over the past few years, I've solved a lot of problems just by adding indexes onto a client's database. And some of the things that we can troubleshoot there is reducing and eliminating blocking. If you can get to your data faster, you can reduce the amount of time that it takes for having locks open, and you can reduce blocking. You can resolve deadlocks. If you've got tables that just don't have a really good indexing scheme, where you get lots and lots of scans while you're trying to do lots of inserts or lots of updates, you're going to get lots of deadlocks. A couple new indexes can fix that. You may also, on your OLTP systems, see problems with parallelism. Well, you'll see these problems with parallelism as CX packet weights. And what you want to do is build some indexes that remove some of that. And the same thing goes in for a lot of these other troubleshooting things with weights, as far as the I/O and latching. When you've got issues with getting to your data or having your data locked up in your system, indexing can help with those issues. Now, the next thing that you can do is start to build out a more efficient system. You may have your hardware getting torqued up to peak use. You may have all of your memory committed. You may have all of your CPU committed. You may be seeing issues with the storage subsystem, and you can solve a lot of these problems. Not really solve, but you can mitigate a lot of these problems by having an efficient system. And having that efficient system can be achieved through having the CPU, the memory, and the storage working less by having the right indexes in place. And by having those right indexes in place, you can extend the life cycle of your platform. One situation I ran into with a client is they had a very poor subsystem. The subsystem turned out to be that they had these 4 drives that are on their system. But when we dug a little bit deeper, these 4 drives were really just 2 drives that were mirrored, and the whole thing was all partitioned out. Well, by adding the right indexes in place, we were able to extend the life of that subsystem and give these guys that were working on it a lot of their life back until they were able to, of course, we wanted to get a new subsystem there, and we eventually did that, but the right indexing helped us gave us a bridge to get to the point where they could do that.
The other thing is teamwork. And I never really thought about this as far as an indexing, why you would index. And the teamwork kind of comes with this noisy neighbor thing. And we hear a lot of this when people talk about Azure with the noisy neighbor. And so to prevent you from having noisy neighbor in Azure, they'll kill off queries that are taking up too many resources. Well, this same thing does happen on our on-premise SQL servers. We just don't really pay attention to it too much. I had a client once where they had an application, and one day they finally put in that extra ticket into this application, and the whole thing shut down, the whole SQL server, by adding one more row. And so they're like, all right, we need to isolate this onto its own machine. We need to give it 8 cores of CPU. We need to throw out there, I think it was like 16 gigs of RAM. And I took a look at the database, and the database was 250 megabytes in size. So, let me look at this a little bit closer. So we looked at the table, and there's 26,000 records in the table. Now, indexing wasn't the only problem that they had. The guy that was the chief developer didn't want his developers to have to think too hard about how data was set up. So he built on top of, it was like 50 tables. He had about 200 views that he had on top of that, so that people could get exactly what they wanted without having to think. So we added some indexes in, cleaned a little bit of that up, the views up, and of course, then that database could sit with all the other ones because it was tiny. 26,000 records wasn't a huge thing. But by looking at indexing, we can decrease the amount of memory that a database potentially uses and increase the number of databases that we can have running smoothly on a SQL Server instance. So those are the main reasons why we want to index. As DBAs and sysadmins, when we're working with a platform, this is what we want to get out of it. We want that at 5 o'clock on Friday, that nobody's going to call us until Monday. And maybe that they don't call us until like Wednesday because, well, we're just going to coast through Monday and Tuesday. So when it comes to indexing, though, what can we index? Well, we index data. And we do this by looking at what it is that we need to do to get to the data that we need and provide an access path for that data. Now, within SQL Server, the way that this materializes is there's 6 ways. There is clusters or clustered indexes. If you don't have a clustered index, then you just have a heap. There is the non-clustered indexes. There is the new column store index, which was new to SQL Server 2012. The full text index, spatial indexes, and XML indexes. Now, this gives you pretty much a way to make it faster to get to pretty much every type of data that you have in SQL Server. You can't really index images, but with full text, you can index the textual information that comes with indexes. So pretty much what you need to get to, you can get to with an index, and you can make it faster. Now, as I mentioned, there's clusters and heaps. The heap is just the data dropped on the disk in the order in which you're throwing it into SQL Server. It may not be in the same order depending upon how the pages are laid out for the database, but it's just the data's being put on the disk. There is no sort to it. SQL Server doesn't infer any sort to it. If it needs to look for any data within that heap, it is going to look through every single page to get to it. The only exclusion is when it comes to, which I don't have on here. Oh, I do. There we go, is the row ID lookup. If SQL Server actually does know what the row ID is, it can go to a specific page. But that row ID doesn't include anything specific to the data. It just goes and drops it in. Now, there is one problem that can happen with heaps, and, well, there's a few problems, but the main problem that can happen with heaps that people don't pay too much attention to is forwarding records. When you have data that is 10 characters, and you drop it into the table, and then you do an update to it, and now it's going to be 100 characters wide. If there's not enough room where that heap record was previously, it's going to put it somewhere else, and then it's going to leave a pointer telling you where to go and get it. And that's a lot like fragmentation that happens on clustered and non-clustered indexes. And it's one of the things that you have to pay attention to, but we don't see too much. And I'll show you guys how that works in a demo. Now, the next thing is, of course, the clustered indexes. Clustered indexes work off of a B tree where all of the data is sorted within the index. And so all the data is laid down on pages in the sorted order that you tell it. It can be on one or more columns, but the data and all the indexes, it's all stored together. So if you know exactly where to go for a specific value, say it's the sales order ID or the sales header ID, it will go directly down to that data. Now, there can be fragmentation that occurs here. And fragmentation with all indexes, well, with clustered and non-clustered indexes, is basically where if you you just do an update. You do an update where you have too much data for that page. It's going to take half the page and put it somewhere else, and it's going to leave half the page there. The row that you're putting into the page has no bearing on which pieces get put where. It just takes half the page, puts half here, and the other half somewhere over here. And in that way, the pages aren't sequential anymore within SQL Server. Well, physically within SQL Server. Logically, they're still sequential. SQL Server will jump from one to the other and come back. And so with this, when you're accessing the data, you'll do clustered index scans, where you start at the beginning and you go all the way through. The larger the table, the less ideal that is. You can have clustered index seeks, which in most cases is exactly what we want. We want to go exactly to the row that we want to get to. And then the other operation is key lookups. And key lookup happens anytime that you've got an index that can get you most of the way there, and if there's a column or two or more that isn't in the index the non-clustered index that you're using, SQL Server has to go and get that, and it does it through key lookup. Now the third type or the second type actually, because the last two were the first type, is non-clustered. This is still sorted just like clustered indexes are. It's in a B tree where all the values are stored in there in a sort. It only has the key values included. So all of the data that's associated with that row, so if you're sorting a sales order row by customer ID on a non-clustered index, only the customer ID is going to be in there. And it'll keep one other thing in there. It'll keep whatever the clustering key is. And that's kind of important when you're thinking about non-clustered indexes, because if you do end up having a clustered index that's very wide, so say 16 or 32 characters, that's going to be inserted into every single non-clustered index. And I've got a demo where I'll show you how that can be bad. There is one exception when it comes to non-clustered indexes, where data will be stored with the non-clustered index, and that's when you're talking about this, included columns here, which are ways that you can modify some of the indexes. When you're looking at non-clustered indexes, one of the things that you really want to think about when you're building out those indexes is, what is the included columns that I can include in this? And by doing included columns, you provide that ability to go and do a seek across a separate sorted stack of the data, but also have a little bit extra data in there so that you don't have to go back to that clustered index. The other thing that you can do with non-clustered indexes that's extremely powerful that a lot of people miss out on is filtered indexes. Filtered indexes allow you to throw a filter onto a non-clustered index to reduce the number of pages and the amount of data that's going to be in that non-clustered index. When you start to think about tables that get to be in terabytes of size, and you look at your reporting, and you're only reporting on the last, say, 30 days worth of data, wouldn't it be nice if you only had an index that was, instead of having a summary of a terabyte of data, it was maybe 100 megs worth of data. Having to sort through that and pull that data apart is a lot quicker than terabytes worth of data. And so filtered indexes allow you to decrease the amount of data that you're going to go through to increase your performance. It also decreases the amount of maintenance that you need to do as far as fragmentation, as far as it comes to fragmentation, and then also makes it much quicker just to build the index. Yes, sir?
Does that require that you're using literals before you can use filtered indexes?
Yes. Filtered indexes do have one requirement. Well, they have a few requirements, but one very specific one is that you do need to include the literals that you're using for the where statement in the query that you're using. And basically, actually in my demo, I'll show you how that works. Because basically, if SQL Server doesn't know exactly what the filter is, it can't know that, well, for maybe this time it works with the filtered index and maybe next time it might not. So it needs to know exactly that. Now, there's a couple other things that you can do with indexes. You can make them primary keys, which basically allows you to use that as a uniqueifier for the rows. And then there's unique constraints. And the main difference between primary keys and unique constraints is that you can actually have null values in your unique constraints. Now, column store is a new type of index that was introduced with SQL Server 2012. It's basically flipping indexes over on themselves. And basically, instead of having all the data stored as rows, it's taking all of the values in one column and grouping them together. It's taking all the values in another column and grouping those together, and so on and so forth throughout all the columns that are in the column store. It's then putting a compression algorithm on top of all of that to just compress the data down. It's highly compressed. I've seen multiple terabytes worth of data drop down into just a few hundred megabytes. When you're looking at integer-based data, column store is a great solution. Now, there are a few caveats with it. The one is that it's primarily focused on OLAP and data warehousing solutions. With OLTP, there is one big flaw with column store that doesn't work very well on an OLTP type system. And that's the fact that, and I have it on the screen there, is that it's read-only. Once you build a column store index, it is read-only on top of that column store index. Now, fortunately, we've got some evidence that Microsoft is working on that and making that better. With PDW v2 that was just recently released, that read-only has been removed. So as long as you're doing column store as a clustered index, you can do read-write against it. And there are some patterns that Microsoft has released on column store that show how to do read-write against tables that are utilizing column store indexes. And that's basically leveraging partitioning and partition views to push the data in. I see some people nodding because I'm sure they've dealt with that solution. I'm sure that if the lights were a little bit lower, they'd also be smirking because it's a tricky solution. But it works. And that's a key thing, is that it does work. Let's see here. That's the laser. Now, full text. How many people here are using full text? Oh, actually, how many people have ever used full text? Oh, wow, that's way bigger. That's way more than I've seen ever before. How many people are actively using it? Okay, so not so many. How many people have queries where you get wildcard searches on both the front and the back? Okay, that's a little bit fewer than I usually get. Full text is a way to just take documents, index out the contents of those documents so that you can zip through them quicker than you could with, say, just a like comparison within SQL Server. It's also good for doing document searches and digging through things like legal documents. The big area where I use full text with customers is when I'm trying to fix issues where they're having lots of like comparisons and they're using wildcards on both the front and the back. And I've got a demo where I'll show you guys where that can be kind of powerful and useful for improving the performance of queries. It's a very useful indexing tool that I don't actually see with a lot of clients. In 12 years, I think I've seen I've worked with one client that's actually using full text. And so it's something that should be leveraged a lot more than it is. Spatial indexing is new for SQL Server 2012 as well. It basically takes the spatial data types and pulls them apart into grids and multiple layers or levels within a grid hierarchy, so that what you can basically do is find out within that grid which cells would fall under a specific location that that spatial entity consumes. It's probably the most complex out of all of these indexes. We could probably spend half a day talking about it, and you guys would, you'd be bleeding out of your ears just a little bit, but you'd get it. If you're using spatial data types, the geography and the geometry, you definitely want to look at the spatial indexes. We're not going to spend too much time beyond just this slide talking about spatial indexes because it gets deep really fast. The last one is XML indexes. And this gives you that ability to dig into the contents of the XML, look through the multiple look through the elements and the attributes, and get those indexed out. With the release of SQL Server 2012, I believe it was with SP1. It might have been with SU, but I'm pretty sure it was with SP1. They introduced a new type of XML index, and that's the selective index. And that allows you to actually take an query statement and index off of that. That new type of XML indexing is extremely powerful, and that's one of the reasons why Microsoft broke the rule that it usually works with of not including new features with service packs. And then the last thing, if you're going to be looking at indexes, one of the biggest things, and this isn't really an index type, this is a way that you can store your indexes, and it's one that you need to take a look at when you're trying to improve the performance. And that is compression within your indexes. All of your indexes can be compressed. There's two types, there's row and there's page. Row is really great if you have just only integer and decimal type values, because what it's basically going to do is jump through and compress those values. If you have more textual information that's within your database or within that table or that index, you want to take a look at page compression. What page compression is going to do is it's going to take all your strings and it's going to start looking for patterns within them and then replacing those patterns with a dictionary value that reduces the amount of space that a lot of those take up. I have seen using index compression. I've seen in a number of cases where you can get phenomenal index gains or performance gains through just adding in the compression. Because as you're doing the compression, what you're doing is you're reducing the number of pages, which then reduces the amount of work the SQL Server has to do, and you're able to push more data through in a shorter amount of time. And there's a number of times where I've successfully fixed index problems by just adding a little bit of compression. So now that we've gone through all of that, I want to go through some demos that show how all this works. Yes, sir?
You wrote self-performance down there. What about the locking problem? Isn't there a locking problem with that?
A locking problem?
Yeah, don't you lock more rows if it goes to page lock?
You would lock more rows. I've not run into a locking problem with compression.
So if you make a lock page,
Mm-hmm.
then if you're compressed into that page, then
More rows.
is compressed into that page.
Yep.
You will lock more rows.
You would lock more rows. So the basic question is, if you're using page compression, you're going to have more rows per page, and would you lock more rows? Potentially. especially if you're doing page compression. I mean, if you have a page lock. I don't too often do much with enforcing page locks. You can have lock escalation issues. But I probably wouldn't look at, if you're having page locking lock escalation issues, I probably wouldn't look at getting rid of compression. I'd probably look at what the queries are that are running that are causing that escalation to occur. So, all right. So before I jump into the demos, are there any questions? Yes, sir. The full text? The full text has been there for years. I think it's been there, I think I would guess to say SQL Server 7, but I know it's been there since 2000, maybe even longer. There was a rewrite that occurred with SQL Server 2008 that made it significantly better. So the question that I'm answering that you guys hear the answer for, that you didn't hear the question for, is when was full text indexing introduced? Yes? Talk about what? Clustered column store. So right now, the question is, can I talk about clustered column store? So I can a little bit. So right now with SQL Server 2012, you only have column store that's non-clustered. You have to have a clustered index on the table, and then you add the non-clustered column store on top of it. So the only thing I can confirm, because it's the only thing I know, is that with PDW, with V2 that just came out, they have introduced clustered column store. And clustered column store is basically, it's read-write. You only have one copy of the data, and you get all the benefits of column store. Beyond that, was there anything specific you're thinking? Okay. Yeah, I mean, that's the big things. I don't know if it's going to be in SQL Server 2014. I hope. I really hope. I can't imagine why it wouldn't. But it's very cool. It'll give you some interesting indexing options when it comes to SQL Server 2014, if it's there. Other questions? I thought I saw a couple more hands. Yes, sir.
What are some of the cons to doing compression companies? Why would you not want to compress all of it?
So some of the cons on compressing your indexes. Compressing indexes takes up CPU. If you're sitting at about 80-90% CPU utilization, compressing the indexes is going to be a bad idea. You're going to cause another problem to occur. Yes. Yeah, so since you're reducing the number of pages, there's less work that the query itself has to do. But when you're writing the data out, there's going to be more work that you have to do the compression. And then when you're reading the data back out, there's going to be a little bit more that you have to do to retranslate out the data. It's not so much that you want to avoid it, but if you're sitting at pretty high CPU, you're going to want to take some care. The other thing is that you will get, there are two other issues that can come up with compression. One is that you can have data that is so wildly strange and there's no patterns within it that SQL Server will try to compress the page. It can find that it has no compression that happened whatsoever, and so it bails on the compression. And then you're doing work that you don't even need to do. So you definitely want to watch that. I've seen that a couple times. I put together a demo once to create an interesting scenario out of it, and it can rack your SQL Server if there's a ton. I created a scenario once where it was 100% of every single page compression attempt would fail. SQL Server didn't like that. The other issue that you can have is that the difference between the compression sizes, so you could have row compression or page compression, no compression. Sometimes between page compression and row compression, there's no difference in the number of pages, and so there's no need to do that extra effort, because it'll still try that extra effort and see what it can do. So there's one more over here. I'm sure I saw a hand. Or someone was yawning. Okay. Anyone else? Okay, let's look at some demos. So I'll go to 2 here. Okay, so the first thing I want to start with is, I often get the question is, well, why should I even bother to cluster my indexes? what value does it have? There are a few people that have that, let's not ever cluster anything, let's just go with heaps. Heaps can cause some interesting issues to occur. Not really issues, interesting degradations in performance compared to what you're looking for. And so let's build a couple tables. And so what I did is I built this one table. It's got just a column in it, and we're going to play around with this column to show how being clustered or not being clustered can have an effect on the execution plan and how SQL Server behaves. It'll be easy to tell which one's clustered and which one's heaped because it's in the name. And so we'll just do one query real quick here where I can just demonstrate, and I'm pretty sure that I forgot to turn Zoom it back on. We can demonstrate here that if we look at the if we look at the execution plan that's here, this is the one with the heap, and it's using a table scan. If we look at the other query, and in this case, it's also doing just a table scan. So between the two, in this particular scenario, there's no difference when it comes to the clustered indexes and the heap. But it doesn't take a lot of work to get to a point where it starts to matter. And so in this case, I'm just going to do an exists check on that heap table. And if we take a look at the execution plan for that, we do see that it's a little bit, come on, mouse, work with me. There we go. It's a little bit different. And the main difference here is this sort. So when you're doing this exist check, it's running through and finding out which rows exist so I can pass them back through. And when you're doing this exist check with a heap, it needs to sort it so that it can optimize that execution. And it's true that it's only 2% in this case because we're working with a very small set of data. But if you've got two large tables, that 2% can be a large amount of work. And so if you talk to people and they're like, well, heaps don't really matter that much. Yeah, they do, and it doesn't take that much. Because we can just do something simple where what if we wanted to just pull back? As I mentioned, heaps have no sort. So if I want to find one record, and in this case I want to find record 43,665, the early issue that we're going to see here is that between the two of them we have a scan on the heap and a seek on the clustered index. When it comes back to what is the I/O impact of that? And please remember, these are really tiny tables. All my tables are tiny so that the demos go quickly. But it's the difference between 27 IOs and 2 IOs. But imagine if this table was 1,000 times larger. There is no way that with the heap that you're going to be able to reduce that. Well, there is one way. The one way is we could add a non-clustered index that covers that sales order ID, and I'll add it to the clustered index as well, just so it doesn't look too magical. And if we run those two queries again, button that so we can make this bigger. Adding that clustered index, that non-clustered index in there to give you that sorted look through the data, it made it a little bit faster because now you can do an index seek, but there's not enough information in that index seek, so you have to go and take a lookup within the heap in order to get all the information that you want. Of course, we're working off of the primary key here. We're working off the sales order ID in the sales order table. And so with the clustered index, we could have just gone straight to the data. And that's the issue that you're going to see when you're working with heaps, is that you start to get either lots of scans or you end up with lots of row ID lookups. And that has an immediate impact on the I/O. And so the I/O between the two of them is going to be, there's going to be a difference, and it's going to get larger and larger the more data that you have within that heap. Now, when it comes to selecting your clustered indexes, Clustered indexes, the best way that you can do and go and find your clustered indexes is to find a static value within your data. Find something that's extremely narrow. Make sure that it's unique, because if you don't go with unique, SQL Server will go through and find a way to unique your row by adding what it calls the uniqueifier, which is a number between 1 and 2 billion, depending upon how many duplicates of that row exist. And going with something ever-increasing is usually best. Ever-increasing basically means that whenever you add in a new row, it's going to be added on at the end, and it'll just keep adding it on, and it'll keep branching the tree, and you'll get a nice distribution throughout. There's basically 5 patterns for choosing your clustered indexes. There's an int identity sequence, where you're getting that 1, 2, 3, 4, all the way up until infinity, or, well, if you're using int to about 2 billion. That's the one that most people choose. That's the most common way to find clustered indexes out there. It's static, narrow, unique, ever-increasing. You can use surrogate keys. Surrogate keys are sometimes a good way to go, especially if you're dealing with something like a state table. You can use foreign keys, which is basically a primary key from another table. Multiple columns, where multiple columns are paired together. And then the last one, and I kind of put these in the order of which I like them. The one I hate the most is GUIDs, or unique identifiers. And the main reason why I don't like unique identifiers is that they are big. They are 16 characters, well, 16 bytes. And those 16 bytes add up. Earlier, when I was talking about the clustered indexes and non-clustered indexes, I did mention that for every value that's in the non-clustered index that you're indexing, you're going to be including the clustering key. And you include that clustering key so that when it finds, say, JSON in the non-clustered index, it knows that that goes back to, say, customer ID 59. And so it can jump back and it can grab all of that. When we start to take a look at the sizes of these, it doesn't take a lot of rows before indexing choices like using GUIDs start to add a substantial amount of data into your non-clustered indexes and making them quite larger. Now, if you're going to just use an int for your clustering key, the amount of data that you add on when you have 1 billion rows in your table is about 3.8 gigs. It's a little bit of data, but it's not too terrible. When you're talking about big ints, you're going to be looking at about 7 gigabytes of data. And if you're using a GUID, you're then sitting with 15 gigabytes at 1 billion rows of extra data in every single non-clustered index. That's a lot of data that starts to add up very quickly, because that's 12 gigs more data that you have to search through in order to find something within that index, as compared to using an int. Yes? So the uniqueifier is 16 bytes. You don't need to mark it as unique. You should. You should. Because if you don't mark it as unique, then it's going to add the uniqueifier onto it. Oh, the uniqueifier. Sorry, I was thinking unique identifier, because they're so close. They're cousins. Uniqueifier is 4 bits, because it's an integer. And you can have scenarios with uniqueifiers where you run out of the ability to add new duplicate key values. It comes in right about 2 billion when int runs out. I've only heard of it happening once, so it's not a terrible, terrible tragedy. The question, for those that didn't hear, because I forgot to mention it, was how big is the uniqueifier? Yes, sir.
Two more questions. What is the best practice about if you have more columns in your cluster index? What the most distinguished? Where do you place that? Is that in the front or as the last column?
Okay. So the question is, what's the best practice for putting the most distinctive value within a multi-column clustered index? The best practice is to put the most distinct value first. the value that's going to eliminate the most number of columns, you want to put that first. Because you're going to get through the data quicker that way. All three columns would then be added to every single non-clustered index. And I'll actually show you guys how that happens in a couple minutes. So I want to show just one example here with an integer strategy. So let me just create a table with some fruit in it. We'll insert some data. And this is a fairly simple little example, but I just want to show, what happens when we pull it out. So we can get to the fruit that's in there. And the main reason why we want to go with having a clustered index is when we run that, when we actually run it, there we go, it's going to go directly to that one row. And if we look at the plan that's associated with it, if I run it one more time, it's going to give us that index seek. And in most cases, an index seek when we're accessing the data is going to be the most effective. Now, the pattern that I like and I use quite a bit, and I don't see too often being used, because a lot of people go like, okay, I know the integer strategy, and so I'm going to get the identity, the primary key, get it all built out, and I'm good to go. In most cases, that's going to be perfect. The kicker is when you have tables that are related to each other in a parent-child relationship. And so if you've got a table of customers and all your customers have orders, and the way in which your application always and only works is that you never go and look for an order. You always go and find your customer, find his orders, and dig into it that way. Now that's kind of an uncommon pattern, but a really common pattern is to have orders that have details. Almost every single application out there that sells things has orders with detail records. And almost every time that I look at those applications, I see a clustered index on the orders that's on the integer, and I see a clustered index on the details on the integer. The trouble is that you're never going to go and look for details by themselves. You're almost always going to go and look for the order and then all of its details together. And that's kind of where the foreign key pattern comes from. And so let me just show this. Get this table built up. All right. So in this demo, I've built out 3 different tables. Get that help statement out there. I've got just an order header table. So we got an order header table that has the order header. And then I've got 2 sets of detail tables. The top one that's suffixed with ICP is using the int pattern. And so it's going in there and it's using integers in order to, it's clustered indexes on the primary key and the integer. The second one is clustered on the foreign key value. So that order header ID that gets dropped into it, that's the clustering index. And so let me turn on execution plans. We'll run through that. And if we take a look at the first index, what we're seeing is it's doing an index seek. It's doing an index seek on looking for the order headers, but then it's also doing a key lookup to find the rest of the data. And so because it's using the order header non-clustered index to find out where all the orders are, it's got to do this extra step. If we use that foreign key pattern, we just get 2 index seeks and not have to do any additional extra effort. And just taking a look at the I/O between the 2 of them, there is a bit of a difference. Come on, zoom in. There we go. 12 versus, 4 reads. So that's the main points when it comes to looking at clustered indexes. The next set of demos I want to take a look at all deal with non-clustered indexes and moving through the various patterns that are out there that you can use and leverage for non-clustered indexes, the things to look for in order to get the best set of non-clustered indexes. And so the main patterns that we're going to be looking at here is a search pattern, just an index intersection pattern, multiple columns, covering indexes, included columns, filtered indexes, and then some foreign keys. And why indexing foreign keys is extremely important. So to get this started off right, let's build a table. There we go, get that table built. And so we're going to start with just a search for Catherine. And if we do the search for Catherine, it's probably easy to guess that without any indexes on the table besides the clustered index, looking for this person, Catherine, within the table is going to result in an index scan, because there's no way for SQL Server to know how many times Catherine's in there and where she's located. So this is the most basic. So we'll add in an index for first name, because we're looking for Catherine. And I don't know any Catherine, so I'm not really picking on a Catherine. All right, so if we take and we do a search on just Catherine, now that we've got an index on Catherine, and we're just pulling back the contact ID and her first name, and if you recall, contact ID is the primary key, it's the clustered index, and as I mentioned earlier, you do get the clustered index value in the non-clustered index. And so to satisfy this index, we only need to go to the first name index. And we can pull that back out. And we can see that there's only 2 reads. Now, compared to the previous execution where it was 2,866 reads, this is quite the performance improvement. And in a lot of customers that I work with, this is really where you start. And you might want to take a look at a lot of your databases, and you're going to see little problems like this. Now, of course, we want to make things a little bit more difficult. We're going to look for just a specific Catherine. We're going to looking for Catherine Cox. And because Cox wasn't part of, well, the last name isn't part of the non-clustered index, we have to go somewhere else to get that information. And so in this case, what SQL Server is doing is it's going and finding all the Catherines, and then it's going through and checking each Catherine to see if her last name is Cox. And it's doing that with a key lookup. And if we take a look at the reads in this case then are 68. So we went from 2 to 68 by adding in another filter. Okay. Well, we can create an index on last name. We've seen this happen on many of our tables where you add another index and you get this additional, additional index, so we get that index created. We'll run the query on Catherine Cox again. And the execution plan changes. Now, instead of having a key lookup, it's going to last name. And this is one of the indexing things that SQL Server does that a lot of people don't talk about. We talk a lot about index scans. We talk a lot about key lookups. We don't talk a lot about index intersection. What SQL Server can do, if you've got the right indexes there, is have one index that has the first value that you're looking at, have another index that has the other value that you're looking at, take the output of those two, find out where both of them intersect, and return back those results, without having to go to the clustered index to get the results, because it can find everything within 2 non-clustered indexes. And this is probably actually happening on your systems all the time. Of course, that leads into the question, why don't you have an index that has both of those names in it? And we can do that. And if we put them both together, and the one thing I didn't point out here is by doing the index intersection, it was 5 reads. So it was a couple reads to go and get Catherine, it was a couple reads to go and get Cox, and it was 1 IO to go and push them all together. And if we run them both together within one index, we'll just have one index seek, so we don't have that additional operation. And this is the value in doing multi-column non-clustered indexes, is because it can satisfy it all within one index, it only has to do 2 IOs. Now the question might be is, why wouldn't I just do multi-column indexes for absolutely everything and cover all of my different needs? The trick is it may turn out to be that the distinction between the number of Catherines and the number of Johns and the number of Phils, that distribution changes depending upon which name you're going after. And then the Smiths and the Straits and the Carlsons, they have different distributions. There's probably not a lot of Straits in there, because I'm the only one I know, besides my family. But I don't, who knows their family? That distribution is going to be a little bit different, and sometimes it might make more sense to go with, in the index, first name, last name, because in some combinations that's more distinctive, and in other cases last name, first name, and that's more distinctive. And so you can go both ways, and sometimes you don't want to make the decision ahead of time because you know that the distribution is so wonky, and so what you'll do is create 2 separate indexes and go with the index intersection, because you don't get the best performance, but you get the better performance as compared to having multiple multi-column indexes. Now, the one thing that we used to do a lot of before SQL Server 2005 was covering indexes. And covering indexes is any time you take all of the values that a query is going to need and you put them into the key values for your index so that you don't have to do a key lookup. In this case, we're going to be working with an index that is, well, a query that's looking for first name, last name. We're looking for Catherine Cox again with is active as an additional column. And as you might have guessed, we're going to see this key lookup again. And you'll notice that I'm talking about key lookups and I'm trashing them just a little bit. Key lookups are not a terrible operator. They're great if you just need to go every now and then and get just another extra value. The downside is if you have a system that's heavily dependent on doing key lookups, and it's doing them over and over and over again, it's an extra CPU, it's extra I/O, and if it's the way that you're always accessing the data, then you're not using the best index for accessing the data. You're using an adequate index to get to the data, and there's probably a different indexing pattern that's out there. And that's why we look at all these different non-clustered indexes. So if we add in an index that covers for first name, last name, and is active, we can get it back down to an index seek. Now, there is included columns that were introduced in SQL Server, I believe it was 2008, might have been 2005, where you can include different values within an index. So maybe sometimes you're not going to always have is active. Maybe you need to go and get email address instead. You need to get something else. That's where you're going to start pulling in your included columns. And in doing that, you can avoid the need to do key lookups and just do index seeks, and you have more flexibility with your indexes. Because as we've gone through all of these indexes, if you've noticed, we keep adding more and more and more indexes. And the more indexes that you have on the table, the more maintenance you have to do whenever you have data that changes. And if we take a look at how many indexes we have right now, on this table with all of the work that we've done, we've got six indexes on it. Now, 6 indexes isn't necessarily terrible. When I only have 5 columns in my table, 6 indexes, right? 6 indexes might be excessive. And so you're going to want to do index consolidation, and that's why you have to think about all these different types of indexes and how SQL Server can use and leverage them, because we've got this is active one. We've got the one with the included columns. We've got the first name, last name, and we've got a first name index. What if we wiped out some of these indexes? And first we'll take a look at these indexes and see that, right now they're all doing seeks, and as we've talked, seeks are better than some of the other plans that we can come up with. And if we take a look at the I/O, we see 3 and 2 and 2, if I didn't cover them up with my arrow. But if we get rid of just half of the indexes that are out there, can we still get good performance? And that's the I/O for getting rid of those. But let's take a look and run those queries one more time. And just to reiterate, whoops, each one of these is doing an index seek still. And the I/O did go up a little bit, but when it comes to choosing your indexes and figuring out what exactly you need, you do have to think about that whole thing that you hear consultants say all the time, well, it kind of depends. And you do have to make those trade-offs, because you don't want 100 indexes on a table that's got 90 columns. It might interfere with your load times. So the next thing is putting clustered indexes on, putting non-clustered indexes on foreign keys. This is something that I've seen take down a number of systems, and it's a simple little thing. So let's build out a table here and figure out what I didn't get highlighted. There we go. So that table's built out. And if we look and see what the max customer is right now, the max customer is 701. And the way that these two tables are set up is that there's a customer table and there's a sales order header table. And this goes back to where I first started talking about, what if the way your application works is that you always go by customer and then bring back all of his sales orders before you do any other work. Well, say you need to delete one of those customers and you want to pull one of them out. And in this case, I don't have, on the customer ID column in the sales order, I don't have any indexing on that. So if I go to delete customer 701, let's bring out that execution plan. We can run that. And we're going to see that there's a very large number here, well, compared to the other number. 4,513 reads. So to delete one record, I have to look at 4,513 different pages within SQL Server. And these pages might be being used by other customers. And what would happen if you're doing this kind of an operation against other customers? And the reason why you have so many of these reads is that in order to do that clustered index delete, it's got to go and check in the sales order header table to make sure that none of the customers are related to that one record that you want to get rid of. So you want to get rid of one record, but we're checking every single other record because there's no index on customer ID in the sales order table to make sure that, well, it's not going to cause a referential integrity issue. And I've seen that cause deadlocks galore in a few systems where people had to spend most of their Christmases being online versus being at home with their families. So it can be kind of a problem. So let's create an index on customer ID, and we'll figure out what the most recent number is. So we have number 700. And if we now delete customer 700, we're going to see that there's a substantial change in the number of IOs. And in the system that I worked on where this was the problem, this stopped them from having deadlocks completely. And by the next Christmas, they forgot that they used to have to stick around for Christmas and work the entire time. And when I pointed it out, they're like, oh, this is kind of cool. And if we take a look at the execution plan, it's just the index seek for going against the sales order header table. Now, let's go back to the slides, because there's actually still a few slides we need to get through. So we did talk about the cluster indexes. I'm going to skip asking for questions right now, just so that we can make sure that we get through the rest of the content. And so, but the big thing to remember is when we're talking about what we can index, you can really index anything. You can index everything, but you don't really want to. It's all about getting the right indexes in place. And the more familiar you are with all of your choices, the better indexing that you're going to be able to do. And when we talk about how we should index, if you talk to consultants, they're going to say, just use the force. It'll just work. And some of the things that they'll run and they'll get done on your systems, that makes it look like magic. But the reality is they're all going to the same place. They're all looking at your metadata. They're all looking at the indexing statistics. And they're using some of the tools that SQL Server has baked in that will tell you what you need to index. There's a lot of distrust that happens with the tools that are out there for SQL Server. But if you take a look at what they do and what's available with them, you're going to find out that they give you some exceptional information. So when you're looking at indexing metadata, you can find things about heaps, duplicate indexes, overlapping indexes, reverse indexes. You can look for indexes that have non-clustered indexes that have lob data in it. Lob data is all the documents and the large data types that you have in your indexes. You don't necessarily want that in non-clustered indexes because now you've got these large values that you're repeating over and over and over again. And in those cases, you want to do a key lookup. And you can look for unindexed foreign keys. When you're looking at the index stats, you can look for unused indexes, slow indexes, indexes that have heavy reads and writes, indexes that are causing blocking, any bloated indexes or fragmented indexes. And then when it comes to the tools, there's a lot of tools that are out there. You can start with the missing indexes, which you can get out of both the DMVs and the plan cache. The plan cache has a few other things. If you're using filtered indexes, I don't think we'll have time for the filtered index demo, but there is a way that you can check the plan cache of SQL Server to make sure that when you're doing filtered indexes on your system, that SQL Server is using them. Because SQL Server will report into the plan cache every single time you could use a filtered index, but you didn't. You can find unmatched, and that's your unmatched indexes. You can also look for implicit conversions where you're doing scans against indexes because maybe you're using a bad data type on those. And then there's Database Engine Tuning Advisor, which is a great tool for taking a workload from your environment and running it through and getting a whole list of indexes that would potentially help improve performance. And of course, there is a number of community resources out there that have index analysis scripts, SP Blitz, index analysis, and this would be SP Help Index. But rather than talk about this too much more, let's look at some demos. I started working with the index statistics that's out there and available probably about 3 years ago, and I've been amazed at the amount of information that SQL Server actually provides for you that you can leverage to find out how to index. So we can first start off with, there's this index columns, and then if you take sys tables, you take sys columns, you can start to dig in and find out where things are like your heaps. So if you want to find out where heaps are, that information is out there and available. But it becomes a little bit interesting when you start looking at duplicate indexes. Duplicate indexes are indexes that are out there, they're in your environment, and they're exactly the same as another index. And I can tell you for a fact that SQL Server is not going to use 3 indexes that are exactly the same. It's going to pick one of them. It may shift around on which one it's going to use, depending upon where your statistics are for that index. But at any one time, it's only going to use one of them. So let's start with building out a table here. And in this table, I put in 2 indexes that, of course, look exactly the same. Now, you can go into the metadata for the indexes. All the stuff is stored within SQL Server, and you can find out all of the columns that go with an index. And so I'm not going to try and explain the script, because that'll take like 10 minutes. But let me just show you what you can find out by going into the index metadata. Just very simply, you can find out which indexes are duplicated. It's a very nice script to run when I'm going out to a client and doing some performance analysis, and we're dealing with indexes. I run this first because this will give me some things that make me look magical, like day 1. And then I tell them, dude, it took like 3 hours. Of course, if you remember back, I said non-clustered indexes include the clustering key within the non-clustered index. So what that means is that when you're physically storing the index on your machine, well, not your machine, hopefully your production server is not on your laptop, but if it is, move it. But when you're storing it on the server, the clustering key and the non-clustered key are going to be stored together. So let me create 2 more indexes. And these 2 indexes look a little bit different. Come on, zoom. Zoom, there we go. First name. We already had 2 indexes that include first name. Person ID. One index, it's an included column. The other, it's a key column. For both of those indexes, it's on a table where person ID is the clustered index for the table. So, dbcc-ind is a dbcc command that will tell you which pages are associated with an index. And so what I'm going to do is I'm going to pull out that index and show you guys the list of all the first pages. And so the first page for the first index is 114,000. So we're going to put that right there. We'll pull out the second one. Let's pull out that third one. And what I'm doing here is I'm using dbcc-ind to find out what the first page of all four of these indexes, non-clustered indexes that we created. And then I'm going to use dbcc page to bring back the information that's on that page. So dbcc page will let you look at what a page, any page that's within SQL Server. It'll let you take a look at it. So if I run all three of those and take a look at the first page, how many people think that the indexes are going to be completely identical? Ooh. I figured I'd get one hand. So, first page of four indexes. All four of those indexes have first name. Some of them have person ID as included. Some of them have person ID as a key column. And some of them have person ID as just the clustered indexing key that would be included. And so if we look at the first one, we've got first name A, Scott, Aaron, person ID 8631, 18722, 18723. Let's just start going down here. 12, 126, 249, 10, 1815. Are you guys seeing that these are exactly the same? Right? Is anyone seeing a difference? So those are the first two indexes that were created. The ones that we saw from the metadata were exactly the same. But what if we look at the other two? 8361, 18722, 18723, 12, 126, 249. Yeah, dyslexia made my math skills suck. Look at the bottom one here. This is the fourth index. Does anybody see a difference between any of these indexes so far? All right, they are exactly the same. Now, wouldn't it be cool if when we're doing the duplicate indexes script that we can pull that back out? And the cool thing is, if we go to the metadata, SQL Server will tell us that there are duplicates. So all this data is there. And the first one gives you some interesting duplicates. They give you some of the obvious ones that people may have caught. This will give you all of the duplicate indexes, down to the physical layer. And that's kind of important. Now, if we get to thinking about how we did the duplicate keys, the duplicate indexes, if we can find duplicate indexes, couldn't we then take foreign keys and look at the columns that are in the foreign keys and find out if there's indexes that match the foreign keys? Well, we're looking at the index metadata, and the answer is yes. We can find out that the AdventureWorks database does an absolutely terrible job of building indexes on foreign keys, because it's missing quite a few. And when you're looking at these, you look at the ones that have the most rows in that parent-child relationship, because if you have to do a scan against 121,000 records, you may end up having some performance problems. You don't necessarily have to do an index on every single one of them, because when you get down to the ones down here, where it's 3 rows, well, if that's not indexed, it's probably going to scan that index anyways. And so you can look at that kind of stuff. The more interesting things, though, comes when you start to look at what SQL Server is telling you about the indexes and how they're being used. Because you can find the indexes that SQL Server is having trouble loading quickly. You can find the indexes that SQL Server isn't using or is only lightly using. You get basically 3 main DMVs that give you this information. Index usage stats, so how many plans are executing that are using those indexes. Index operational stats, how are these indexes being used throughout all of SQL Server, not just which plans are using it, but more to the tune of how many pages are being accessed, how much locking is occurring, how much blocking is occurring. Index physical stats is going to tell you what the level of fragmentation is and how that data is laid out on SQL Server. And stats properties telling you the level of change rate within those indexes. So you can easily find out unused indexes, and any index that doesn't come back from the index usage stats isn't being used. And if we go to the AdventureWorks database, we're going to get a much better result set. So we can get the indexes that aren't being used. But we want to find more interesting information. We want to find out indexes that are only being used a little bit. And so all of that information is out there. And we'll jump into it here. And we can see that we've got some indexes that are only being used a little bit. Now, wouldn't it be nice if we just go and delete all the indexes that aren't being used a little, right? Because if it's not being used a lot, who cares? Let's get rid of it. Don't take that approach. It's a very bad approach. The reason why it's a bad approach is it may turn out that that index is only being used for one exceptionally important process, like the morning import. And by deleting that index, the morning import now is going to take, instead of 5 minutes, is going to take 4 hours. I got to teach somebody that lesson. The statistics? Yes. So all the index usage stats and all the DMVs have different periods under which it is pulling back information. And this changes from time to time. Depending upon how you're using it. So when you restart SQL Server, all these stats are blown away. They're gone. When you rebuild the index, most of the stats are blown away. And then if you drop the index, amazingly, the stats go with it. You can find heavily used indexes. Same kind of thing. Look for the indexes that are being used the most. You can look for write-heavy indexes, so indexes that are being used a lot, that you're making lots of modifications to them, but you're hardly ever using them at all. And so we'll let this one finish in a second here. In a second, it'll finish. Okay, so while that's digging through, I'm going to show you something else. The other thing is, I talked a little bit about lightly used indexes. So if you want an index, you want to get rid of it, you want to find out what the quality of the plans or the statements are that are using that index. You don't want to just delete it because it's not being used a lot, right? So what if you could ask SQL Server, hey, where'd you get used the last? What SQL statement did this index actually get used on? And you can do that. You can do that by querying the plan cache and asking it what indexes it's using. And you do that by taking the index name. So I ran a query here that used that index. It's using this index, that query. And we'll highlight this whole bit here and run that. And you can pull that information out. Because in the execution plans, it tells you which indexes it's using. And so you can, if it's in the execution plans, it's being stored in the DMVs within SQL Server, and you can dig into and pull that information out. Now, we're sitting at about 45 seconds left. Obviously, I could go on and on about this, but we're kind of running out of time. So I'm going to go through the wrap-up slides. If people have questions, please come and see me afterwards. I can give you access to all sorts of other indexing resources. Those community resources that I talk about on the slide deck here, take a look at those, and you're going to find that they can give you some great indexing suggestions and help you automate your processes. If you're not using Database Engine Tuning Advisor or the missing index DMVs, use them because they are free indexing suggestions that if you want to find them out for yourself, it's going to take you a few hours. So why not use what SQL Server is giving you so you can go to the more interesting things? But remember just to review this information because you want to be the index whisperer. And yeah. All right. So that's all I have for you guys for today. Please, if you want to get a hold of me afterwards, just coming up, I can give you a business card. Thank you.